Let us revise the D block elements. Now these are the elements in which the filling of electrons takes place. Filling of electrons takes place in the penultimate D subshell, and the penultimate means the second last shell. And D block elements have a general valence shell electronic configuration. Electronic configuration is n-1 D 1 to 10 and ns 1 to 2, where n is greater than or equals to 4. Now D block of the periodic table consists of 3 complete rows, each containing 10 elements. Each containing 10 elements, because the D subshell can accommodate maximum 10 electrons. Now the first row of the D block is called 3D series, and the name is given 3D series because the filling takes place in the penultimate 3D subshell. So first row of the D block is called 3D series, and with the electronic configuration of argon 3D 1 to 10 and 4s 1 to 2. And the configuration of these 10 elements of the 3D series is very, very important, because the other physical properties of the D block elements, especially 3D series, related with the electronic configuration. Now the first element is called scandium, and its electronic configuration is argon 3D 1 4s2. Second element is titanium. It has electronic configuration of argon 3d2 4s2. The third element is vanadium, argon 3d3 4s2. Then we have a chromium, argon 3d5 4s1. Chromium is an exception, and both the subshells are half filled because they have extra stability. Next is manganese with the electronic configuration of argon 3d5 4s2. Then we have iron, electronic configuration argon 3d6 4s2. Then we have a cobalt, argon 3d7 4s2. Nickel, argon 3d8 4s2. Then we have another exception, copper, in which the D subshell is fully filled and the half subshell is 4s. So this copper also has an extra stability in the ground state. And the last element of the 3D series is zinc, which has both fully filled 3d10 and 4s2. Now all D block elements are metals. All D block elements are metals. And form positively charged metal cations. Positively charged metal cations. In the 3D series, a filling of electrons first takes place in 4s, then in 3D, and the removal of electrons also takes place also takes place first from the 4s and then from the 3d. So filling and removal both takes place in the 4s first, then in 3d. And these d block elements are also called transition metals. Transition metals when the elements in the ground state or in the most common oxidation state, most common oxidation states have incompletely filled a D subshell. Now group 12 of the periodic table, group 12, zinc, cadmium and mercury are not considered as transition elements, are not considered as transition elements or transition metals, as they have a fully filled D subshell in the ground state as well as in their common oxidation state of +2. The next point is that all D block elements have very high melting point, and this is due to a strong interatomic forces of attraction. Interatomic forces of attraction, they have a strong metallic bonding involving both n-1d and ns electrons. And from left to right, in the 3D series, as the number of unpaired electrons in the D subshell, unpaired electrons increases, interatomic forces of attraction increases, and the melting point increases. Now, after chromium, pairing starts in the D subshell, pairing starts, and the interatomic forces of attraction decreases and the melting point decreases. So in the 3D series, chromium has the highest melting point and zinc has the lowest melting point. Now next point is the D block elements have high enthalpy of atomization. And this also depends on the interatomic forces of attraction and the involvement of n-1d and ns electrons. So enthalpy of atomization also increases from scandium to chromium and then decreases from iron to zinc. So zinc has the lowest enthalpy of atomization due to a weak interatomic forces of attraction, as both 3D and 4s subshells are fully filled. And the 5D series elements have a strong metal-metal bond present. So they have strong interatomic forces of attraction and hence higher melting point and enthalpy of atomization than 3D or 4D series elements. For example, in group 6, the increasing melting point order is, it's a chromium, then molybdenum and tungsten. Tungsten has the highest melting point in the whole periodic table. The next is, which is very, very important property of D block elements, that is called the oxidation states. So we'll discuss important points about the oxidation states. This is an abbreviation we use. Now the first point is that the common oxidation state of the 3D series elements is +2, which is obtained by using two electrons from the 4s subshell. Next point is that the 3D series elements shows variable oxidation states. They show more than one oxidation state. Variable oxidation state due to the comparable energy of a 3D and the 4s subshell. As a result, both 4s and the 3D electrons participates in the bond formation. Next point, that the oxidation state increases from +3 in scandium to +4 in titanium to +7 in manganese, as the number of electrons in the 3D subshell increases. Now after manganese, a pairing starts in the D subshell. In the 3D subshell, therefore the number of electrons available for bonding decreases, oxidation state decreases, and the +2 oxidation state becomes more stable in the second half of the 3D series. In second half of the 3D series, as the size decreases. Next point is that the 3D series elements shows their highest oxidation states with oxygen and fluorine. These are the two most electronegative elements in the periodic table. Two most electronegative elements in the periodic table. And the 3D series elements shows their highest oxidation states in oxometal anions. Oxometal anions, for example, we have a chromate, we have a dichromate, we have a permanganate, where the oxygen forms a double bond with the metal atom, double bond with the metal atom. The next point is as the oxidation state increases, these are three very important points. So as the oxidation state increases, first point, that the oxidizing power increases. And the second point, the covalent character increases, polarizing power increases. And the third point, the acidic nature increases, acidic strength increases. So higher oxidation states are more acidic, more oxidizing, and more covalent. For example, this is Mn2O7. This oxide of manganese with +7 is most acidic. Then we have a MnO2 where manganese shows +4, and then we have a MnO where manganese shows +2. The next point is that scandium is the transition element which does not show variable oxidation state, which does not show a variable oxidation states. The next point is the chromium 2 plus is a strong oxidizing agent, is a strong reducing agent, means it loses one electron easily, loses one electron easily to attain a chromium 3 plus, which has a stable half-filled T2G3 configuration. And that's why chromium 2 plus is a strong reducing agent, whereas the manganese 3 plus is a strong oxidizing agent. Strong oxidizing agent gains 1 electrons to attain stable half-filled (3d5) in manganese 2 plus. Now the next is that transition metals and their compounds also show color and paramagnetism, and this is due to the presence of one or more unpaired electrons. But zinc 2 plus compounds are white. Zinc plus 2 compounds are white and diamagnetic due to the absence of unpaired electrons. So to find out whether the unpaired electron present or not present, you write the electronic configuration. If you have any unpaired electron present, then the compound will show color and will also show paramagnetism. Paramagnetism means they are attracted towards the magnetic field, and the degree of paramagnetism means how strongly the substance is attracted. Degree of paramagnetism is given by magnetic moment, and the symbol is mu and is given by n into n plus 2 a Bohr magneton, where n stands for the number of unpaired electrons. So if you have unpaired electron present, mu will have a non-zero value. If you have all electrons paired, then the magnetic moment will have a zero value. So these are some properties of the d block elements.